All right, so we're talking about electricity today, electromagnetism. So there was an experiment that happened. But before I do that, I forgot to mention, so here is the magnetic field that you've probably seen for a really long time. You've probably seen it in elementary school or whatever. And so you'll notice that you have some field lines, right? And so you have these field lines going on here. Those are going to be important. The way field lines are will be important in a little bit. So what happened was this. There was an experiment that happened one time. And a scientist was setting up an experiment, and he had electrical wire set up, and he had current that was flowing through it, but he happened to have his compass right near that. And when he turned on the electric current in that circuit, he noticed the compass changed from the direction of the poles from the earth and aligned itself with that electric current. And so that the compass actually went. So if current was going this way, okay, all of a sudden the compass moved perpendicular to it. And so what the scientists had found out just from that was that when current runs through a wire, you get a magnetic field. So magnetic fields are created when electric current occurs. So if you take that idea and you can say, oh, I can move a compass. Well, after a while, you could start saying, well, what if I can get the timing down? And if I can get that compass to spin a little bit and then turn off the current, and then it keeps going, and then turn it on again and keep going. What you could try to do is get something constantly spinning if you're bored and need something to do, but curious about it. So that's what actually built to the first electric motor. So if you look at what a motor is, it is a bunch of wire wrapped around a magnet, okay, or a piece of metal. And then, so you'll have an electric magnet or electromagnet, and then you're going to have outside of it a solid state magnet. So what happens when the current runs through? When the current runs through the coils, it's going to make this big, strong, the current's going to create a magnetic field, and because it's coiled up, it's even easier, where the current is going to start directing itself through that coil and be strong on one side to be north and strong on the other side to be south. So if you have north on top and you have a north solid state magnet, what's going to happen? They're going to repel, right? So the north is going to want to push away from the other north, and it's going to be attracted to the south. So you have pushing away. You have that top of the coil pushing away from north because it's repelling, and being pulled towards the south because it's attracted to it. Well, what they figured out is if I put little gaps in the wires, as soon as that north is supposed to get to the south and it would normally stop, we're going to turn off the electricity. And what the magnet would end up doing is, or the inner part of the magnet would keep spinning. It's got some momentum to it. It's spinning. We got angular momentum. So it would spin a little bit past that south. And as soon as it went past the south, the wires would engage again, but this time the bottom part that was getting closer to the north, now that would be attracted. It would turn into being attracted to it, and that would get attracted to it, all right, and get pushed away again. So what the gap in the wires did was it made a nice timing for it, and what you end up with was your first electromotor. So the electric motors are basically coils of wire, an electromagnet, solid state magnets on the outside, and then gaps to make the timing so it just continuously spins, okay? And so we talked about some of the uses for electromagnets there as well. All right, so let's talk about a magnetic field. Okay, so this is what they wanted to know, is if we have that magnetic field there, will it create electricity? They wanted to go the opposite direction. So would we be able to put a wire next to a magnet and then get electric current, go the opposite way? So what they figured out was this. If you set a wire next to these magnetic fields and did nothing, nothing would happen. But if you moved the magnetic field along these magnetic field lines, nothing would happen. However, if you crossed, so if I took a wire and I crossed these magnetic field lines, all of a sudden current would go on that electric wire. So if I took the wire, cross it, those magnetic field lines, I would get electric current on that wire. So what they figured out is if I have current, I can create a magnetic field. And if I have a changing magnetic field by crossing lines, I could get electric current. Okay? So what you end up with is this. If you look at that motor and go the other way, you can take an electric motor and basically turn it into a power generator. Okay? Because if you think about those magnetic fields going on, okay, from the solid state magnet going back and forth, if I personally spin those wires and those coils, it will constantly cross the magnetic field lines, okay, and I can continuously add electric current onto the wire. And this is how we get electricity. All power supplies that we get, except for solar, is this idea. We are using some type of energy to spin electric wires so that they keep crossing magnetic fields and we can get current going out to a battery as it shows here or wherever. Okay, so if you think about how you get power, whether it be a nuclear power plant, power plant is taking the energy from nuclear heat, turning water into steam to spin turbines, okay, and the turbines are these little coils of wire that are going to spin inside the magnetic fields, okay? Wind power is the same thing, except they're using wind to spin the turbines. Any type of power except for solar is doing this type of thing. The Hoover Dam is taking water to spin the turbines, okay? And so that's how we get most of our electricity today. All right, so we just said that stationary magnet didn't work, but when they started moving those coils of wire across field lines, it did work. All right, so remember this. Electric current creates electromagnetic fields. Changes in electric currents changes in electromagnetic fields create current. Okay, so they're almost the same, but they're not exactly. Current creates electromagnetic fields. Okay, changes in electromagnetic fields create current. All right, now let's take this idea of electromagnetic fields and changes electromagnetic fields and apply it to what a transformer does. So if I have current and I have wire wrapped around an iron core, it can create a really strong electromagnetic field. Okay, the wire has to be insulated. You can't have uninsulated wire. So if I have a couple coils around one end of that wire, and then I have a little box of that iron core, and then on the other side, I have a different number of coils. What's going to happen is this. So I have primary versus secondary. If I send current through that coil in one direction, okay, that's going to create one type of magnetic field. But that magnetic field will never change, okay, because the current didn't change, nothing would happen. However, if I have the current go through the wire in one direction, and then I go the opposite direction, so I go back and forth, back and forth, back and forth with that current, well, what's going to happen is you'll have a magnetic field going in one direction, and then the magnetic field changes, goes the opposite direction, back and forth, back and forth. So you now have a changing magnetic field. So then when you go look at the secondary coils, if you have a changing magnetic field, you're going to create electric current on these wires. And so now you're going to have current going out of that secondary current from the primary. Okay, so you have to have it changing. You cannot hook up direct current. You cannot do DC current and use a transformer, because there would be no changing magnetic field. There would be no current going along the secondary. Okay, this is the big issue that Thomas Edison had. Thomas Edison created those first turbines and created electric current, and he did it in Wall Street, right along Wall Street. He did it to all the big bankers so he could get more money. But the problem was this: he believed in DC current. He only believed in having a constant flow of electricity, which meant he could not use transformers. Okay, so he'd only send DC power out, and that meant he could send current, and it was only a city block or two, that he could sell electricity to, because direct current doesn't travel that far. Transformers will help you send electricity really far distances. Okay, so let's get back to these coils here. If you look at this transformer here, if I have 2 coils on one side and I have 3 coils on the other side, the ratio of coils will be equal to the ratio of the voltages. Okay, so my ratio here is 2 to 3. So let's say that I give it 120 volts in my input. For my primary coils, I have 120 volts across that part of it. Well, 2 to 3 means my output on the other side would be 180. To keep that ratio the same, I'd end up getting a secondary voltage of 180 volts. So what I was able to do, I'm not taking away, I'm not creating new energy, okay? I'm actually going to lose some current, but my voltage will go up. So my voltage would go up, and I went from 120 volts to 180 volts because I used a transformer. All right, we call that a step-up transformer. All right, so here, looking at this is the idea of how we get electricity now. Let's say we have a power plant over here, and let's say that it sends across those wires about 35,000 volts. That's a lot of voltage, okay? Now it's going to go across these power lines. Current, really high current is bad to send far distances because you're going to lose a lot of that electricity. So you want to keep the current really, really, really small. All right, so they're going to step up the voltage to send really far distances. Let's say now the current is around 68,000 volts. So when you see the really, really large, high power lines, those have about 68,000 volts on them. And they have to go really far distances. Okay? But then you'll see substations. In substations, what they do is they will drop down the 68,000 volts and they'll lower to, say, 13,000 volts. So the 13,000 volts would not be able to travel as far a distance, but it's a little bit safer. You don't want to have 68,000 volts running through your neighborhood. So the 13,000 volts is going to be able to travel a farther distance into neighborhoods, okay? But 13,000 volts, that wouldn't be able to be traveling across the country, okay? Those 13,000 volts would then go to your neighborhood and hit a power transformer drum, whether it be something that you see up top near your house, or you probably see the green boxes. In most neighborhoods now, it's going to be that green box on the ground that's completely covered up, and that's your transformer, and that just feeds a handful of houses. And that's going to have another step down. It's going to step down from 13,000 volts to, say, 120 to get into your house, okay? Because we can work off 120 volts, all right? So the idea is this, though. The power is always the same. We don't create or destroy energy with transformers. But when we have to send voltage or current a really far distance, we want to have a really small amount of power. So if we have a really small amount of power, we need to have a really high amount of voltage, which is why those power lines are at 68,000 volts. Okay, when you get to your house and it's only coming from a really close distance of a transformer, now you don't want to have really, really high voltages to deal with. You want to have 120 volts to deal with. In the United States of America, we have 120 volts. So it's going to step it down, the voltage, and jack up the current, because the current doesn't have to travel as far a distance. Okay, so the current times voltage of the really high power lines will still be equal to the current times voltage inside our houses. It's just easier for that current to travel farther distances if it's a really small current and a high voltage. And then the opposite in our house, we don't mind having a high current because it's not going to go very far, and we want to have a much lower voltage so that we're safe.